Thank you very much for this kind introduction. Do you hear me? Can you hear me? I've been pondering a lot before I got here. What should I talk about? I'm here at the center of the Institute on Complex Systems. And when I went through the list of prior speakers, and also when I looked at what other people affiliated with the center do, it's very data-driven, very statistical. And we at the center, the Research Center for Open Digital Innovation, also do that kind of work. But it's about complex systems, so I thought I might share some work that is inspired by complexity theory, and in particular by Stuart Kaufman, who worked on complex system in biology and tried to explain the fitness of genes. Well, how I'm going to translate that into the open and digital innovation context, I'll hopefully be able to explain or share with you in a bit. You already said everything about me, so I thought I have to briefly introduce myself. A question. And did you hear about open innovation before you came to that talk? How many have heard of that phenomenon before? Oh, so it's quite a bit. Yeah, so I'm really into this new way of innovating on creating value. And there is a term, open innovation, that I've been trying to get my head around for a while. I'm right now at Purdue in Indiana, but as you can hear, I have an accent. I'm not from Indiana right now, given the political situation. I also have to emphasize that I'm not from Indiana. I came there, as you mentioned, about 3 years ago, and I founded the research center, which is really interdisciplinary. It's in a discovery park of Purdue. And if there's time, I can also show you a few other faces that are affiliated with the center. I'm a boundary spanner. I have an engineering background. I also have a management degree. I've been spanning boundaries between different disciplines, and I've also spent time in industry. I've held industry positions. Well, I learned a lot about how innovation actually works, and I'm really valuable to have that experience. Yeah, so I'm going to give you a brief introduction why I'm actually studying this, why it matters from a practical point of view, and then I have two studies that I'm going to share with you. One is a simulation study, as was mentioned in the introduction, and afterwards I'm going to share some ongoing experimentation that I'm doing. Well, two things that motivate my work. One is open innovation, the fact that we have very distributed forms of innovating, that firms have started to open their boundaries and work with other organizations, with universities, and also make use of tools like crowdsourcing on innovation contests. And at the same time that we have a digital transformation, we do have social media that change the way we communicate. We have mobile technologies. We have Internet of Things that changes a way how smart things become, and also changes how organizations create values. Well, that was inspired almost more than 10 years ago when Henry Chesbrough from UC Berkeley wrote the book Open Innovation, and I started to work with him just around that time or a little later to understand whether this phenomenon is, what this phenomenon is, and also whether this phenomenon is actually sustainable. Just to remind ourselves, open innovation originally was really a firm level concept, and this is the famous funnel he usually put up there. So you have on the left-hand side closed innovation. You see there is the innovation pipeline, and usually in the past, organization would start a lot of projects, test them, and then after a while they realize, this project doesn't really fit our business model, and they would stop it. So these are in kind of red dots, the unused assets, so to speak. And in contrast to that, the open innovation model, where you purposefully, so I have to emphasize that, make use of outside knowledge flows, where you use knowledge from others, from clouds, etc., to accelerate your innovation process, or where you give source code or technologies away. So the open source movement is one of those topics that also made open innovation popular. Without going into detail, we looked into a recent study among executives whether open innovation really still matters for the large firms. So we did a study, Henry and I, on large firms in United States and Europe to see whether open innovation is adopted. And we found that about 78% of the firms practice some form of open innovation. Only a small percentage have abandoned it. They have increased their financial investment in it, and they have also hired new people. They hired open innovation managers, community managers, etc., and create new jobs, new roles in that field. And it's saying, okay, it does really matter. Well, having said that, the term openness has been used in so many ways. We talk about open innovation as a firm-level strategy. We talk about open platforms and platform-based ecosystems. We talk about open data. We talk about open science. And there is actually a community of scholars in the field of open innovation where we argue about what's open, what's closed. I could continue with this discussion, but I'm not going to do that because we'll never end that seminar. I'm just going to say that we have new forms of organizing innovation, and they're more fluid, they're more decentralized, they're more self-organizing, and individuals matter much more than in the past because they can take actions in a new way. This is also very much driven or enacted with new technologies. So new forms that I'm particularly interested in is competitive crowds, communities, where the 5 technologies that I mentioned here really play an important role. And they're not just enabling, as some management scholars, they actually enact. They're kind of an affordance for people and allow them to create new artifacts. So I could talk about 4 different studies where I'll deal with developed communities that work in these digital environments and create new artifacts. So one could be an open source. I worked on an OpenStack platform with one of my PhD students. Also work on open data contest. That's something I hopefully can share later. Also work on some open science project. But what I want to focus on is develop communities of platforms and digital platforms. And I'm sure everybody of you is just carrying around a very important platform, 2 competing platforms, iOS and Android. And they have really changed the way value is created in the phone business. And so this is a study that I've been performing with my collaborators. One is Esteve Almiral. He's a professor of information system at Desada Business School. And then also Anne Maishak. She's a professor in the data science group at USC. The downside of upwards driving assimilation of the interplay between developer strategies and platform complexity and performance. Yes. Platforms have become a very popular mode for organizing the development and the distribution of software. Having said that, platforms not only play a role in software. If you look into, for example, John Deere, does anybody know John Deere? Yeah, agriculture, right? Now they have also become platforms that offer apps for the farmers to manage their farm and integrate also other applications. So what does a platform do? If I was an economist, I would say it's a 2-sided market. I have on the one hand the developer communities, on the other hand I have the customer community or crowds, and basically they bring those 2 sides together. So I'm looking at that as a new organizational form because the platform owner, those that originate the platform, if I'm looking at Apple or if I look at Google Android, they coordinate development activities of their software developers. And the platform performance very much hangs on the performance of the apps developed, not so much at the platform. Actually, the platform itself just has a core functionality, but for user, it really matters in the end what this application does. It varies across platform, but it's really how good the applications are, that what defines the performance of an application. And we have that in video games. We do have social media platform, Facebook. We do have Salesforce, Firefox, or WordPress templates you could think of also being a platform. I'm looking at that more from an engineering point of view, also being an engineer, and look at it from the architectural point of view, how platforms are designed. And platform architecture, so to speak, that finds the structures, how the developers can extend the platform, what they can do on the platform, what they can change, how they can program, etc. And nowadays, so to speak, software development kits and APIs play an important role. Anybody of you a little bit into app development or So they really, really define what the application can do. And if you look nowadays in these platforms, there are thousands of toolkits, libraries, subroutines, some very specific for a platform, other platform independent. And you also have kind of platform agnostic modules like Google Maps, for example, that you can integrate. And app developers just mesh this all up. So the design, they create the design space, they create the design space that the developers can use and create and creatively design the applications. Yeah, so today it's really about how do I design those software development kits, because and the subroutines, the application programming interfaces, because they define how well my platform in the end is going to be, how well performing it will. So there's a big discussion in the literature about the platform complexity. And I'm looking at two aspects of platform complexity. There are more. One is design interdependence, and the other one is design constraints. We're going to talk about that in a little bit more detail. But there, on the one hand, there are people who say, you know, platform should have low complexity, because if it's very complex, if there's high interdependence, then it really increases the load of a developer, and if the game fails, for example, if a game developer is adding an application to a game. On the other hand, there are people that say, hey, actually, you need to have some complexity, because that's needed in order to differentiate yourself. Because if everything is completely modular, it's so easy to copy, and then all the apps just look the same, because you can't really creatively remix and match those different applications. Well, I'm arguing that part of that controversy is because developers actually have different ways of working with the software development kits and with the development space. And that actually affects that interplay. There's some developers that just basically go the worst way, and that just built the tool, an app they've seen before, so like here in gaming solitaire. And the others, like Pokemon Go or Angry Birds, I don't know whether you're into games, you know, they really think of new features using location-based services, etc., and say, hey, I'm trying something really new. And that might really excite the customer. But that is also risky. So because it hasn't been tested before, other application developers haven't tried it before. So I'm arguing that there are two types of apps that are on the platform. I'm calling them path-dependent apps. It's, you know, inspired by evolutionary economy. Economists saying, you know, you build on what you've done in the past, what you know, and then you incrementally improve that. And it's a safer choice. So if you're an app developer, you just basically, you know, improve a little bit what you've done, facelift, you try to remove your bugs, etc. On the other hand, you can say, hey, I'm trying something really new. I'm challenging the status quo. I'm basically going ahead and offering a really, truly novel application. So the research question that we're asking here is, you know, how do developers' risk preferences shape the relationship between platform complexity and platform performance? And I think even among you, there are some people that are more willing to take risk, and others that would prefer the safer mode and say, and just, you know, incrementally improve my application. There's one thing that affects whether you take risk or not, and that's to do with your aspirations. So the work on aspirations and performance goals that shape the way we take risk. And it's interestingly, we think that we're very complex people, but actually our heuristic is pretty trivial. So there's our aspiration point. I want to be among the average, or I want to be among the top in my class. I want to be the top in my team. I want to be the top football player. And if you're below your aspiration point, you take risk. And if you're above, you don't change that much. So that is also something that matters for our developers on application platforms. So they have different strategies. They're more have higher aspirations, they have lower aspirations. And app development is also not a one-time shot. Actually, if you develop an app, you go through several iterations. You have the first release, you have the second release, etc. So throughout that process, you basically always compare yourself, and you process the competitive information about others. And what I put here is like the iOS top app charts. And I've worked with app developers, and there's also studies about app developers, right? That really matters for them, because they want to be up there on the rankings. That is really important. So they basically process that competitive information and engage in a race. And based on that, they then decide to take risks. Well, there are two types of aspiration response profile, as I call it. And we're going to talk about in a little later how that actually shapes what those application developers do. So we have such rankings on IIS. We have that also on Airbnb. I don't know whether you use Airbnb. Anybody renting out the house? Do? Just users? Nobody, so to speak, a developer here. But anyways, I've done it, and I tell you, I want to make sure that my flat is really among the top picks, because otherwise I'm not going to get any user, right? Nobody's going to pick and rent my place. So you are really looking into those rankings, and you try to be among the top, and that can be really engaged, look like a race at some stage. Well, let's go back to complexity and what I mean by complexity. So I mentioned two dimensions. One is design interdependence and design constraints. So what I showed here, and I don't know whether you're into software program, but this is a dependency graph. So you see there are lots of dependencies, and when you have a software that shows there's really a high interdependence between the different design elements. Actually, that definition is inspired by modularity work, and I'm going to say Carlise Baldwin from Harvard Business School. And her work is just great. She studied modularity in physical systems and basically defined interdependence as a degree in which a change in one component affects the functioning of another component. And because of that, also the overall system. So you have those multiple interdependencies and these nonlinear effects that lead to design interdependence. So if you're, for example, now a programmer, develop a game for a gaming platform, you change something in your animation layer, but then you forget to make a change in the data access layer, and then your game fails. Or if the platform changes the API or another design component that you use on the platform, your game basically fails. We have a lot of layered architectures today, and more. So tools that can be used by the developers. Because of that, we have often greater design interdependence, sometimes even outside of the control of the platform. Well, what's the implication for performance? So one thing, the positive thing is if you have low design interdependence, you don't have to worry about those dependencies. You can just change the animation layer and your program still going to work. Your app is still going to work. So you don't actually, every time you update your app, you innovate it, so to speak, you improve it, you don't have to go through all your dependencies and think about what's going to break, etc. So that's the positive side. So it eases the remixing, etc. The negative is if there is no dependencies, it's quite transparent for other application developers, for others around there, how you can get a better performance, because there's this new feature and that basically sticks out. It's a new visualization. And if you then you can just copy it and you might also benefit from it, because it's not the real, untypical, atypical combination that you can do, because there is not really dependency. So there are some studies actually that say, you need to have some degree of interdependence to actually have the differentiation among your app developers. And some platforms want that for one reason. They want to have same-site network effects. So they want that this one killer app, the unicorn, is attracting more and more applications. But if you have all these unicorns, then the problem is that your whole platform, so to speak, goes down. So you also want to make sure that you have a sufficient balance, what we then call same-site network effects. Well, so there's a positive and a negative side. But the second element is design constraints. I put up that earlier so to explain that. So for example, if an app developer says you can't use this particular API, or you have to use that visualization framework, etc., and it's quite obvious if you compare, for example, Apple with Google Android. It's, the one is requiring more, features to be used. So say they don't allow the developers to change it, so it's fixed. So they impose a design constraint, make it mandatory, and are not allowing to change that. Okay, again, there are positive and negative sides. Low degree of design independence. If you can do what you want, you have the autonomy, you can creatively experiment. And we saw that on Google Android when we had, I don't know, 2 years ago, all these news going around, all this, fragmentation of designs, that there's no joint, look and feel. That's That's then the negative implication that you get from that experimentation. So that's why you have that challenge as a platform owner to say, do I want to have a design constraint or to have one image or visualization design for the customer, or do I want to basically constrain it, but then I reduce the autonomy and the developer feels like he's not able to change as much. Well, this actually is what I just described, this application development process where I'm going through different iterations. That can be also reinterpreted as a search across a fitness landscape. Does anybody of you know of a fitness landscape? Okay. So the NK model, the most important, so to speak, instrument or idea of the NK model is a fitness landscape. And I plotted that for you. I tried to do that in a 3D way, but in reality, it's actually an n-dimensional space. And you can think of the application development process as a search across a fitness landscape. And each position in that landscape, so to speak, represents a design combination. So what kind of application design you use, what animation feature, what data API you use, etc. And then with that particular design combination, there is a fitness value associated. And that fitness value, in my context, is the performance of the app, the number of downloads the app gets. So an agent is a developer, so to speak. He or she searches across that landscape. And what she's trying to do is she's trying to get to the top of the hill, to the highest peak in the landscape, because that is the design alternative with the highest performance, with the highest number of downloads that she could achieve. So in the NK model, you have design elements. So you have a decision vector here. I just used this 6-dimensional one. You have 6 things that you can change. And could relate to the different layers of a platform. And it's a very abstract and stylistic way of representing that because it's only 0 and 1. So it's a different state. So you can only say on or off. And then you have different search processes. Just to clarify what it means, what a neighbor means in a landscape. So one move from one decision alternative or design alternative to the next. It's just by one Hamming distance. So if I have here a combination of 4 zeros and then a 1, and then I move 1 Hamming distance further, this is where I would move to the next design alternative. That has been used, originally it's been developed to describe how genes mutate and how genes or the organism develops in a certain fitness level or performance level. But it's been also used in physics, in glasses, and it's been very influential also in the management work to represent how organizations change or how architectures and design architectures change. For example, Franken used that also to describe modularity of a system and how a design changes the overall system performance. So what we're going to do, we're going to place all our developers of a platform in that design space, in that fitness landscape, and they all search for a higher fitness landscape. So follow me to go to that kind of abstract level way of thinking and to understand how the developer strategies affect the performance of a platform. There are 2 different ways of searching across that landscape. One is hill climbing. Like, you go up the hill and you basically, go one step further. So you just move by 1 Hamming distance all the time. So you look around and you look for the next peak. And then if there's a peak, you move there. If there's no peak around you, you just settle. And the other would be a long jump. You basically jump and you randomly change some decision elements in a variable. So that's what I meant with, you try something new in your design. Pokemon, for example, added location-based service, etc. And you randomly do that without having information whether it actually works in the real world or not. Some developers do both. Not every new release of an application is a path-creating design, not a really radical change. So they really have to think deeply, should I really now completely overhaul my application, or just going to do a, so to speak, hill climbing move and just incrementally improve my app? So every time that I make that decision, It's the aspiration that influences them whether they go for a path-dependent or a path-creating move. So again, path-dependent, that's risk-averse, that's incremental. Path-creating, you're more risk-taking and you take more risk. So that depends on your aspirations and how you process the competitive informational landscape. Before we talk about this, just to introduce complexity now into that landscape. So here you have a landscape that only has one peak. But that's a really smooth landscape. So this is where you have loner dependence. You can just walk up there. It's very easy. And so here, that basically there's no dependencies between the different decision elements. And here's a record one. Record that's like high interdependence. So you have here two dependencies. One decision element is dependent among two other decision elements. And that also influences the overall performance. So you see there are all these deep valleys and hill. There are more hills, there are more peaks. So you would assume that in such a landscape, you really need to jump more often to get to a peak, because otherwise you get basically trapped in a local optima and you don't get to the peak that you could have. And this is really the challenge when it comes to design independence. Also explains a little bit the controversy, because if you have high independence, there are a few people that could differentiate themselves. But it's also risky because you need to jump, because with a hill climbing move, you're not going to get anywhere. Design constraints are basically you can change the design elements. Well, so now coming back to the aspirations, and that's basically how we model the search of our developers across the fitness landscape. So there's lots of work on aspiration. When we had a Nobel Prize in prospect theories. You know, we also learned a lot about how our reference points or aspirations affect when we take risky choices. Well, what we see in competitive environments like tournaments, games like football, soccer, etc., or when people gamble, there are kind of two types of aspiration points. So you either really want to be the leader, you want to be at the top, and if you're not there, you're going to take risk. You really set your target really high. Or you're more a satisfying developer. By the way, that term's influenced by Syed and March, the behavioral theory. So you want to have stability. You're more interested in a common target level. And, you know, the average is just fine. But if you fall below the average, then you take a little bit more risk. Now, I want everybody here to think about themselves a little bit, how they act, you know, when they think of degrees and grades, etc. Because there might be some of you think, you know, I just want to be the A+ students. And I said, you know, I'm just going to be fine if I basically pass, etc. Right? So we see that also with game developers or app developers in general, that you have some that really, really want to be the top app that gets all the applications, want to be the Pokemon Go. And then there are others that say, I'm just fine with the number of users that I have, and I don't need to take more risk. There's another dimension of how they process information is how responsive are they to the most recent information. So you have actually access nowadays real time about the downloads of your application. But you might also use, so to speak, the performance data on prior releases. And interestingly, we observe that, for example, outside of app development, when you look at teams in soccer and football, they basically use the rankings from last year or the year before to pick, you know, the points that they want to have. So they're not actually looking at the, you know, most recent. They might go back even several years. And the same with the stock market, or, you know, some organizational routines also make people basically go back into history instead of actually looking at the most recent information. Well, so in the end, you could basically also combine that, come up with a portfolio. But you have basically those upwards driving, really forward-looking developers that really want to shape, you know, the application, and you have those that are more laid back, the satisfying one, and backward-looking. You might think of a few apps yourself. Yeah. 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 Yeah, exactly. So how do you know? So basically, you could say our developers are all only locally intelligent. They can only assess whether kind of a small design improvement can gain them basically more users. Otherwise, they have to jump. And then it's risky. They have no idea. And some would argue you can actually assess that up front and then go back, but you actually have to launch your application to the market, right? So, and then you realize does it actually hit on the market or not, and then you basically, you know, need to see what's going to happen. Yeah. Yes. Right. Platform design space is constantly changing, but it's actually not. Like not all the time. So you mean, you know, you're not going to change all the time the APIs, etc. You're not going to change it all the time. But what is changing is the design alternative. And think of this fitness landscape. In the end, it's 2 power 16, all the potential design alternatives. That's kind of a, you know, representation of all the potential design alternatives that an app developer could take. But again, you're completely right. NK is very abstract, and it's a, on purpose, more stylistic way of looking at things, right? But it's not, it's the platform design space, so to speak. And for there, every time an agent moves, they change their design alternative every time they have a new design. If they just hill climb, they basically settle at a certain point. Yeah, now why did we actually do simulations? Why do we think it's actually a complex system that has emerging behavior? Because what I just described all the time was the behavior of an individual developer, and like looking across the design space and say, how can I remix the different design elements? Well, you know, as the crowd, let's say the developer crowd, and we have several thousands of app developers on a platform, as they move along, you know, they also start to perform better. And then each individual developer, you know, they compare themselves, and then they're also the decision to take risk is very much dependent on how the overall crowd is evolving. So we have that emerging bottom-up behavior that also then changes the behavior of an individual developer. And if you think nowadays, you know, there's not just one app release, there are several releases. We assume that there are between 10 to 25. Then you definitely have a lot of emerging behaviors. So what we do in our simulation, we change 4 parameters. So it's a simple model. It's a very simple and stylistic model. We look into aspiration profile, and there are 2 things we change. The aspiration point is like, do they want to be at the top? Are they only taking more risk if they fall below the median? And the other thing is the design interdependence. How interdependent is the design space? And how many design constraints does the platform owner impose on the developers? We then assume that one platform has kind of the same type of developers. They attract the same kind of developers that are either more forward-looking and upwards driving, or they're more laid back, to compare the different platforms at this point in time and to give an overview. So what we did is we used the NK model originally developed by Kaufman, and that was also actually available at C++. The code is still available. Open source. We adapted that. We basically incorporate the idea of aspirations, aspiration points, etc. Also, now we have more computational power. We have more ability to actually to simulate. So n is in our case 16. Then we assume that you know, each design alternative has a fitness value, and the overall platform fitness, so to speak, platform performance is the aggregation of that. We have here path creation, as I said, is modeled as a long jump, similar to Leventhal 1997. We assume that they cannot go back, and then we have the hill climbing, we just move just one Hamming distance along. Then we have kind of a fixed component of risk, so how many long jumps they have, so we also keep that constant. And then a simple behavioral rule: if they fall below the performance target associated with the aspiration point, they jump, and if they're above, they don't move. And this again is the iterative kind of development process of our developers. So they make a design choice, and then they look for the performance discrepancy. They see, how do I now perform right now in comparison to the other developers? And then they design their app again. And then we go on over time. And if they basically have exhausted their long jumps, they're over risk, they settle. Or when when overall the simulation ends. So this is kind of the important point in time where they judge themselves in comparison to other developers. Those are the 4 things we changed: design independence, design constraint, aspiration point, and responsiveness. So, and overall, we ran about 200 million experiments. We used Amazon Web Service, so it was possible to do that. So we had first a control experiment. We basically have developers that have no competitive aspirations. And then we have a set of experiments that look into the design interdependence and the effect of aspiration points, and also the responses of the time, so how quickly they adjust the aspirations. Then we have a second control experiment where we also introduce design constraints. So we fix a few of the design elements. And then we ran also the treatment conditions where we changed the aspiration response profile and the design interdependence. I have to say we also did some robustness check. We modeled, because right now we have a simple, basically step function for the aspiration response profile. Below, jump, above, steady. We also did a probabilistic models based on some other empirical studies and found similar results. So let's just look at some of the results. It's an abstract simulation. So here you see the design interdependence on the one hand, and here of the platform performance, which basically is the mean across 500 experiments that we ran for each condition. What you see, so here you have the base case. Those are developers with no aspiration. You see high design independence, the lower also the platform performance as expected. Then we have 2 other lines here. One is the red line here is the upwards driving, those that really want to get to the top. And the blue line is those that just are satisfying. And what is kind of interesting is you would assume someone who takes a lot of risk and would also ultimately lead to high performance, but it's actually not good. So at a certain level of design interdependencies, it's better to have these satisfying developers that outperform the upwards driving developers. So equal levels or even higher platform performance if you have satisfying developers or developers with satisfying aspiration point. So that's one of the first findings. And we looked then into the distribution, what's happening here? Why is that happening? And so what you see is that we get kind of 2 populations. So here the black line are the upwards driving. So we have only a few of the stars, and then the rest basically has a much lower performance. That is basically the fragmentation that you then also observe in some of the case studies, that a few basically manage to attract all the kind of customers, and the others are really, off, they don't make it. That's kind of the red-green effect. So you have a lot of racing, and because of that racing, and because of the fact that then they constantly compare themselves with the current performance, they take too much risk, and then the population shifts. So you create inequalities, so to speak. So that is one thing. Then the next thing we change is how quickly do they respond? Do they look at the most recent ranking, so to speak, or do they basically go respond slower and adjust their performance target not right away, but rather look at ratings a few iterations before? And what you see here is we also have a flip. So what we look here into these simulations, really transition points, and what we find is the upwards driving ones, those with the red lines, those that want to get to the top, they actually perform better now than the satisfying. And actually the satisfying, there's a response delay with 25 iterations. They're just as bad as those that have no competitive aspirations at all. So you could argue that time matters a lot. It counteracts, so to speak, this negative effect of having high aspirations because of the delay, because they're not getting into that race. So delay in adaptation leads to a situation where a platform with upwards driving developers perform better than platforms with application developers that are more satisfying. This could also explain why some platforms actually delay the release. Some have completely removed it or actually on purpose delay that. And if you have really a slow response time or delayed information, then having just satisfying developers that don't really take risks, damp complexity really has a negative effect. The final thing we changed was we looked into design constraints. And as you would assume, design constraints overall reduce the platform of the performance because you have less design elements to change. You're basically stuck, so you have to work your way around. Think you basically work in a design space. You can only change 4 elements out of the rest. So here we went down to keeping 6 fixed out of 16. And what we found, one is like the shift downward, but we also see that actually there is an offsetting effect. So you here see this peak coming up. So at a higher degree of design interdependence, both upwards driving and also satisfying developers perform actually better. And the higher the constraints, the more interdependency is needed. So it shifts to the right-hand side to get better platform performance. To summarize that, up to a moderate level of design interdependence, high and low aspiration points offset the negative implication of design constraints. And this offsetting effect is particularly strong around 5, 7 K as it is design interdependence. And that transition point shifts to the right. So actually design constraints can help developers flourish if there's also design interdependent, explaining why some of the platforms actually enable design constraints. So what is actually happening here? It kind of removes inequalities. Only if I have K15, I have these inequalities. But on the other hand, design constraints overcome that racing because it reduces, so to speak, the design space. You have less variables to change, and it also then less risky to actually fall deeply if you take a risky choice. Okay, I know that was very abstract. You're still following me? Trying to? So let me kind of summarize what we kind of find. Like upwards driving developers can cause low platform performance. So if you have those high aspirational developers that want to develop the killer app on platforms with moderate to high design independence, that can actually lower the platforms. They perform worse than satisfying developers that just want to go with the pack, so to speak. Delayed response can actually counteract that effect. So both characteristics, the aspiration point and the responsiveness, like time really matters and affects the relationship, the design interdependence and platform performance. And at the same, we also feel that design constraints can be offset, through the aspiration design independence. So design constraints remove to some extent the inequalities that you generate when you have the star performance. And the more design constraints, the more interdependence you need. So now someone might ask, why is it actually happening? What's going on there? We turned that in a paper in some propositions. So one proposition is if a developer has satisfying an aspiration response by all degrees of design independence may lead to greater platform performance. And the second would be if they have upwards driving response profile, higher design independence may lead to lower platform performance. And the reason for this is this kind of self-reinforcing mechanism that's going on there because everybody is being better off, and you create a kind of a red queen race, and over time, then you basically create this small number of app developers. Proposition 2 would be if upwards driving developers delay their response to competitive information, a higher degree of design interdependence may lead to higher platform performance. And this positive interaction effect saturate at a kind of medium degree of design interdependence. So really here the time comes into play. In the past, I was always saying slow response, slow adaptation of aspiration response profile is negative. We find if you actually look into the interplay with design interdependence, it is actually good. And then finally, also 2 proposition on design constraints. If developers have an upwards driving aspiration profile, then high design constraints may actually offset the negative performance implication of moderate to high design interdependence. So, yeah? High aspiration are the only. Yeah, it's the top. It's the top, and that's. We also did a robustness check where we basically took 5% and 10%, and we found similar results. But in that simulation, it's really if they fall below the top, they basically jump. It's like studies. Shapira did that also on managers that were in the games, and they basically really picked the leader as their aspiration point. Yeah. Oh, it in a sense it helped the high upwards drivers. So for the like it did change. So let me just go back. So here you see the red one. And so you mean, yeah, the curve for them didn't change. That's correct, right? Yeah. Mm-hmm. Right. Exactly. Exactly. Right. Right. Limitations, yes. I mean, there are limitations. It's a really abstract model. It's an NK simulation. You have 0 and 1 that you change. Well, what is interesting is more about the patterns, and rather than trying to now nail it down to very hard fact empirical work, but that is actually needed. So I encourage others to do that. But it's very hard to measure aspiration points. So we need neuroscientists that actually measure that, because you can only infer that from behavior. There's also what we do not include as a survival point analysis. We're very much focused on the aspiration point. So future work could also look into the survival point, because that's another thing that actually then affects the decision whether they're going to leave, because our developers did not leave. So they're going to stay there and going to stay until the end. Even though it's an abstract simulation, there is guidelines that we can give for platform owners that design platforms. So it's really important that they design their workspace in the light of the strategies of the developers. So you might basically attract those that want to be the killer app developer. If you have that, you need to basically be very careful how you deal with design interdependence. Often design interdependence can only be reduced to kind of moderate level. You can go actually have it completely modular, but there is also design constraints. So in a sense, what do you basically prescribe? And there is also then the delay of information that you can influence. And actually, some degree of design interdependence is actually recommended if you have a satisfying developer. In the end, we cannot say that platform complexity is good or bad. It really depends very much on the aspiration response profile of the developers. That's it for the first study. Are there any questions? Yeah. Yeah, so in a sense, that's a good question. Like, what if you have both on a platform, right? So do you basically design, in a sense, one workspace for the other? That's one way, and that's actually to some extent also happening. And you could take that further and go, in the end, what do you do to address the needs of both, right? So right now, in a sense, if you have, you can do that, and some platforms do that for the heavy developers that are more in the core. You give them more freedom than others that have really strict rules, right? From open source, for example. Mm-hmm. Oh, it's a very good point in our reviewers, by the way. The reviewers pointed about that. So in a sense, we make the assumption that you have performance and independence. And for platforms that actually address all industries, they're really industry independent, you can make that assumption because the market space is really so big. We had a simulation where we also modeled kind of industries, subsectors and components, etc. We found similar effects. Actually, it was stronger because in a sense, you will compare yourself through with your basically peers from the same industry, right? Actually, we're planning to take that model also further. What you describe as a kind of real ecosystem where you assume that there is actually dependencies in the downloads as well, right? But usually we'd assume that the market size is so big on a platform that you don't have that. Okay. Yeah, it's thousands. I use thousands. You could also add more to that, right? Mm-hmm. Okay, if there are no further questions, something completely different. And again, not statistically, not big data, because I decided not to present that work, but something that is more experimental, more action-oriented, so to speak. We do a range of quasi-experimental studies at my center. That's about open data app development. So again, app development, again on a platform, but this platform, this time we designed ourselves. And we looked into the role of transparency as a design choice. So that was also motivated by the fact that, open data has become an important source for innovation, for mesh-up designs, etc. Also, the emergence of standards, made it easier for application developers to develop open data applications, and in particular, mesh-ups. So mesh-ups is a pretty complex, so to speak, task because you mesh up different design elements, you visualize them, you include data visualizations, and today, an innovation contest has become a very dominant mode to ignite developers to come up with great ideas and mix up these different open data sources and create interactive applications that help the citizens. So what you see here is an app where you can go and look for alternative fueling stations, and there are applications in many areas. We basically addressed the following issues. So first of all, what's the objective of a contest? So in a contest, originally, the idea behind is I create competition, and because of that competition, you increase rivalry and you increase the incentive to create outlier solutions, to take risk. And you don't want to actually see other solutions because in the end, you only want to create the outliers that have a really novel performance. So that's the idea of an innovation contest. But that's actually against the idea of reuse. And even in the world of open data, and here quoting an open data catalyst out there, saying, we don't want to have just greenfield projects where they basically start from scratch and work on a new open data project. Actually, we should inspire them to augment prior and existing solutions, reuse prior solutions that have been developed by other developers, because then we'll actually foster innovation. So that's what the practical practitioners say out there, but that's very much in line, actually, also with the literature that says, innovation is a cumulative process. It's actually about reuse of others' ideas and solutions. And only then you create those really novel, those outlier innovations that have both some standard components, but also some atypical components. So both reuse and experimentation actually work at the same time. That's what the literature says us. But the question then is, in a contest, would argue there's competition, and if I see other solutions, then you would just copy someone else's code rather than try to creatively reuse. So there's the literature on creativity and design that suggests that actually access to existing solutions can inspire or support in developer to be more innovative and more creative. But it might also trigger too much copying. So there's, again, a controversy. On the one hand, they say it's good, and on the other hand, they say, no, actually, they're just going to copy from the other solutions because, and then they're cognitive fixation. They don't know how to move on their own way. So we then ask the question, how can I actually use transparency as a design principle to foster innovation performance, to make to inspire reuse for innovation rather than just imitation? And we look into two types of transparency. One is performance transparency. So you see the rankings of others, so similar to what we've just been talking about. And that also leads to risk taking, as we've just been talking about. But you can also solution transparency. So the argument would be that solution transparency leads to reuse, copying, but it might also foster more creative reuse. Our argument is that both together, if I know what the well-performing solution is, then I also inspire developers to move away from what they do right now, from what they're cognitively fixated on, and do both reuse, but also creatively experiment. So we designed a system that has performance transparency that triggers social comparison processes. So you see the percentile ratings in 4 dimensions. It's anonymous because we don't want to have any social herding, that I'm basically doing what everybody does, popularity. And we also provide them the scores at the same time so that they have all the same conditions. And then there's also solution transparency, so they get access to the actual code and the running application, and they can, in each round of a contest, explore those others. And with that, we ran on campus in a pilot study hackathon. So you see that they hacked and they get their they get the transparency, and then the hack, and then there's again transparency. Oh, and that's basically on the system. I'm not going to show the whole architecture and everything. It's just one part of the screens they see when they log into the community platform. So they see anonymous to hackers, and then they can click on show detail, and they can explore the score, and then they can also go to GitHub, and they can actually click on the running application. Yeah, what we then looked into, we ran a pilot. It was a pilot only here. I think it's a small data set with only 10. And we looked into the reuse. We looked into how similar is the code. So, and we also looked into what did I click on. So we installed an algorithm for that. And we used an existing code cloning technique that used the structural and also the semantic similarities for analysis to see how similar they are. And it gave us the opportunity to measure real reuse and also individual experimentation, so to speak, what is their own code. And here it's just some, click behavior, just descriptive, and you see, yes, they really have upward social comparison. They gonna go for the top. They're gonna explore that. That's, by the way, just an example of an application that was developed by one of our developers in the class. I ran it in a class. So 7 open data sets were integrated, and that was an application developed to identify affordable and safe housing in West Lafayette, because you won't believe it, but there are actually in the Purdue area some areas where you really don't want to live because it's a bit scary. And so there was an application that was developed for citizens to do that. And so he included several visualization features. I'm running out of time, so I'm going to rush a little. So what we looked into, does actually technological similarity trigger that they become more similar over time? And in the first round, it didn't look like it does. So there's not really a pattern, but in the second round, it does. So we found that technological similarity triggered also then to them to reuse, because it's more similar and also easier to reuse. So you see on technological similarity stage 2, and then here is stage 3. It's always pairwise measures. This is pairwise similarity score between 0 and 1. We also looked then into how does performance distance actually trigger reuse. What you see here is the performance distance between pairs, and here you see the reuse behavior. And we see, it's interesting, you have those that go for really large distance, they reach for the top, and then we have others that actually go more for smaller distance. Overall, the reuse isn't really that high, so we also have individual experimentation happening. But what triggers reuse is another dimension as well, the technological similarity, because where we find then stronger reuse, that was also then more similar. So both factors apparently seem to matter. Overall, over time, they increase the performance. Our winning solution developed more of their own code, suggesting, you reuse, but to some extent, you also need to really try to develop your own idea over time to pick it to a higher performance. Well, surprise, transparency doesn't really lead to a lot of copying. Overall, they actually reused, but they also added their own code elements. It's not that they just copycat it as you would expect. And in a sense, there's the social comparison process that might then help you to look at a distant or more distant design, but you're not copying the code. You engage something, it's more analogical thinking, you transfer. You might reuse a feature, but you're not copying the code. And yeah, for sure, this is descriptive right now. We've actually completed 3 other treatment conditions already. I'm going to show you the treatment design we're running. And with my computer science students, we also work on measuring the similarity, visual similarity right now, and the functional similarity to actually see whether it's the functional similarity that triggers the reuse. And that would also explain that there's analogical thinking happening. That is an NSF project that I'm running together with some other professors, and just here kind of the treatment setup. We have a control group, then we have a group that gets only performance transparency, and we have a group that gets only solution transparency, and then both. And right now we run that in a lab condition, and then in the end we'll run a large virtual experiment next year with an online community. Well, what I think is also interesting for us now as Purdue, it actually led to also some huge educational content. So Purdue IronHax, that's what it's basically used to run those hackathons, became part of classes. We offer that to master students. And we also run OpenHax, where they actually get real-world experience. And we have some training models before. They all get the training in 4 weeks. They learn a little bit about HTML, CSS, JavaScript, and Google API, and then the 3 and seed 3 libraries. And then they go into the hack. And we have, it's a real world setting. They get real money. They get money from our sponsors. And we have now started, to roll it up in a larger number of classes. That's from my point of view. I only wanted to show you a few more faces. Who's actually behind all this? I mentioned earlier we're an interdisciplinary group. That's true. So we have people from management, information system, but also computer science students, some sociology as well. Here's Deve from Spain as part of the center. Also work with Sun Mate. I don't know whether he's here or wanted to come on the communication group. CNIT and computer science. So these are professors that I'm working with, affiliated with the center. And I mentioned Anne Maishak here from USC is also part of the virtual team, so to speak. Some of my students that work on that, I'm just going to point out a few. So Charles worked with me a lot on the hackathon. And those are my computer science, mechanical engineering students that also work with me. I'm done. No question. That was too fast at the end, right? Too much.
I'm actually curious whether you have any thoughts about the open evaluation, the open solutions, how those might be applied in the context of scientific research in terms of making grants.
Oh, actually, I should have showed the study because I work also in open science a little bit. I mean, and so can you just tell me explicitly the question, whether it's to do with evaluation or whether it's about?
I'm wondering whether either.
In a sense, you could apply the same idea of kind of some reuse would also make it more innovative, right? But on the other hand, you also have the competitive element that people actually don't actually want to share, and that's a bigger issue right now. Would we basically be overcoming that? Because what we found, we looked also into the willingness to share on the scientific infrastructure on NanoHub, and they only share if they also have the feeling that they can protect. So it's not, sharing meaning, it's a continuum. You share, you protect. There also needs to be some ability to, protect some of the things and have the ability to give some control of some elements. So that's a big issue. But open science is also an important topic. But yeah, you can translate some of these ideas. Okay, thank you.